Yeah, that clock keeps ticking till we start up in here. Yeah, that clock keeps ticking till we start up in here. If you came to learn chemistry, you did your part. Time is ticking down, so just be ready, cause it's about to start. When we solving for problems, we solve it information. You know Ben's Chem videos will provide you with equations. Never have to stop and think about it, this the station that will provide you with the chemistry all in relation. If you came to learn chemistry.
Hey, what is up, everybody? Welcome to the Ben's Chem Videos Sunday night live stream. Tonight, we are going to continue our discussion on electrochemistry. I'm really excited about this one. I think this is going to be a great stream. And so, without further ado, I present to you Electrochemistry Volume 7. As always, your feedback is more than welcome. It is highly appreciated and is absolutely essential for the improvement of this show. So to that end, I invite you to type your thoughts in the chat if you're watching this live, or leave a comment if you're watching this as a video. It goes a long way to help steer me in the right direction to improve these streams, to improve my videos and all that stuff. Also, if you're watching live, you can call into the show. There's a link in the description for you to call in using Discord if you want to talk about batteries, which is what we're going to be talking about tonight, mostly. Or just whatever else. I'd be happy to take your call. All right, so we're going to get into this. We're just going to briefly review the content from the previous episode on electrochemistry, which was Electrochemistry Volume 6. So Electrochemistry Volume 6 was all about two things, the Nernst equation and concentration cells. So the Nernst equation, this is shown on your screen right now. And remember, the Nernst equation is what describes the relationship between cell potential and concentration, right? Because up until the point where we introduced the Nernst equation, we were only talking about standard cell potentials, right? Which is when you have standard conditions, which means that the concentrations of all of your aqueous ions are exactly 1 molar. So it's like, what do you do when your concentrations of your aqueous ions are not 1 molar? Well, that's where the Nernst equation comes in. So we did a couple of things with it. We derived the Nernst equation using thermodynamic relationships that we have previously discussed in previous live stream series. And we also solved a problem in which we had to find the cell potential of a voltaic cell containing aqueous solutions of ions that were not 1 molar, non-standard concentration. So that was the Nernst equation. And then we also talked about concentration cells. So shown on your screen here, if I can get my big head out of the way there. This is an example of a concentration cell. Basically, what you have is you have an anode and a cathode that are both made of the same material, in this case, zinc, and the flow of electricity is caused by a difference in concentration, right? Over here in your anode, you have a dilute solution of zinc ion that stimulates the production of more zinc ions. In other words, it stimulates the oxidation of zinc over here in your anode. And then over here in your cathode, you have a very concentrated solution of zinc ions. Having that high concentration of zinc ions stimulates the reduction of those zinc ions into just plain old zinc, which is what happens over here in your cathode. And eventually, the concentration of the dilute solution in your anode will increase. The concentration of your concentrated solution in your cathode will decrease until the concentrations of both of your solutions are equal, at which point there will be no cell potential because there's no difference in concentration and your anode and cathode are of identical material, right? So that's what we talked about in Volume 6. So I highly suggest you check that out. Not necessarily prerequisite for understanding the content of this video tonight, but I recommend watching all of them. And if you would like to watch all of them, there is a playlist called Electrochemistry Live Streams. There's a link, of course, in the description. If you'd like to catch up on your electrochemistry knowledge, I invite you to check that playlist out. All right, so on to tonight's material. Tonight, we are going to be talking all about batteries. Okay, so I actually have a battery right here, so we're going to talk about batteries. So what is a battery? Well, we've spent an awful lot of time in this live stream series talking about voltaic cells, right? Voltaic cell is nothing more than a device that generates electricity from a spontaneous redox reaction. It's composed of two half cells. You've got your anode where oxidation occurs, your cathode where reduction occurs, your salt bridge, everything in between, right? Voltaic cells. And a battery, like this one, is nothing more than a conveniently packaged voltaic cell that acts as a portable source of electricity, right? So this is a voltaic cell. And what the biggest difference between different types of batteries is the particular substances that are being oxidized and the substances that are being reduced. What's your anode, what's your cathode, what's your oxidation half reaction, what's your reduction half reaction. Those are the big differences between various types of batteries. So we're going to talk about those differences in great detail starting right now. So the battery that is probably most familiar with you is called familiar to you is called a dry cell battery. And they're called dry cell batteries because they contain very, very small amounts of liquid water, right? And so what we're looking at here is a diagram of the common, inexpensive dry cell battery, right? And as you can see, it's a pretty simple design here. You've got this zinc case here that acts as your anode. That's where oxidation is occurring. That's shown in this pink color here, right? So zinc is your anode, and then your cathode is a graphite rod. So graphite is a particular allotrope of carbon. It's conductive. It doesn't participate in the redox reaction, but it acts as the cathode. It acts as an electrode, right? A conductive surface that allows electrons to enter the cathode, right? So that's your cathode. And then as far as the actual substances that's undergoing the reduction reaction, what you have is a paste that contains manganese dioxide, and it also contains some ammonium chloride in it. And so in the next slide, what we're going to do is we're going to look at the half reactions associated with the common dry cell battery, and they are as follows. So let me shrink myself down and get out of the way here, right? So as I mentioned just a moment ago, right, the anode is composed of zinc, and so the anode oxidation half reaction is shown here. It's simply the oxidation of zinc to zinc ion, right? And then over in your cathode, right, you have the graphite that's acting as the electrode, but it's the manganese dioxide that's undergoing reduction. It gets reduced to this manganese 3 oxide over here on the product side of the reduction half reaction, right? So it's reduced by ammonium ion, right? And so those are the half reactions that drive the production of electricity in your common dry cell battery. Now, I call it the common dry cell battery. It's just like your standard, inexpensive dry cell battery. But most dry cell batteries have been replaced with a slightly more efficient set of half reactions. And these type of batteries that are sort of improved over the common dry cell battery are called alkaline batteries. So you've probably heard the term alkaline battery before, but perhaps you haven't given much thought to what it means, right? So at this point, we studied acids and bases previously, right? We should know at this point that the term alkaline is a synonym for basic, right? And you have a basic solution, which means that the concentration of hydroxide ions in that solution is greater than the concentration of hydronium ions in that solution. And at 25 degrees Celsius, that means that you would have a pH above 7, right? So there's the refresher on what alkaline means. And they're called alkaline batteries because the redox reaction takes place under alkaline or basic conditions, right? So we can see here that the design of this battery is very, very similar to that common dry cell battery that we looked at just a moment ago. But notice that we have potassium hydroxide, this KOH, right? So that is responsible for these reactions occurring under basic conditions. And of course, if they're occurring under basic conditions, then that means the equations for the half reactions are going to be slightly different than they were in the common dry cell battery. So we're going to take a look at those half reactions here that are associated with the alkaline battery. Again, just give me a second while I move myself out of the way here, right? So again, it's very, very similar to the common dry cell battery. You have the oxidation of zinc, but you have the oxidation of zinc occurring under basic conditions. So instead of being oxidized to just zinc ion, it's oxidized to this zinc hydroxide over here, this ZnOH2 species over here. And notice that the reduction half reaction is very similar, right? You have the reduction of manganese dioxide, and but the product is different because, again, the reaction is occurring under basic conditions. And so you start out with manganese dioxide, And then upon reduction of it, you end up with this manganese oxide hydroxide, this MnOOH species over here. So again, it's very, very similar to the common dry cell battery, but it takes place under basic conditions. And the advantage of the alkaline battery over the common dry cell battery is that they tend to have longer working lives and longer shelf lives. So I think if you look at this, if you look at this battery right here, I don't know if you can read that or not, but it actually says alkaline battery right here. So literally, these two half reactions that are shown on your screen are the exact half reactions that are occurring in a battery like this one here, this D battery that would go into like a flashlight or something like that. All right, so we've talked about dry cell batteries. Now it's time to talk about some more interesting types of batteries. We're going to transition right into talking about rechargeable batteries, right? So the dry cell batteries, they are not rechargeable. So now we're going to talk about rechargeable batteries, starting with the lead acid storage battery. So this battery probably looks fairly familiar to you. The lead acid storage battery is the type of battery that is found in most automobile engines, right? Or connected to most automobiles. You'll find it in most automobiles. You get what I'm trying to say. Most cars have this type of battery, okay? So how does this battery work exactly? Well, as the name implies, it involves the element lead, right? So you have an anode that is made of lead, and then you have a cathode that is made of lead dioxide. This PbO2 would be the chemical formula for that stuff, right? So you have a lead anode, you have a lead oxide cathode, right? And both your anode and your cathode are submerged in a, I think, 30% solution of sulfuric acid, right? So when people talk about battery acid, usually that means they're talking about 30% sulfuric acid, which is pretty, gnarly stuff. It's pretty corrosive. It's not nearly as corrosive and dangerous as like fuming sulfuric acid, or I think it's like 16 molar or something like that. But yeah, 30% sulfuric acid, your anode and your cathode are submerged in that. And that describes one cell, right? But typically in your standard lead acid automobile battery, you have 6 of these cells, 6 of these voltaic cells containing a lead anode and a lead oxide cathode that are connected in series with one another. In series means that the anode of one cell is connected to the cathode of another cell, right? So usually, each of these cells, there are 6 cells in a battery like this usually. Each cell produces 2 volts, and so when you connect them all in series, you get about 12 volts of potential difference produced by your lead acid storage battery. I got a message in the chat from Roberto. It says, I did not know there were batteries. How many volts is your alkaline battery? Good question. I think this probably puts out around 1.5 volt. Yeah, it actually says it right here. It says it's 1.5 volts. I don't know if you can read that or not. This D battery puts out 1.5 volts, right? So, and of course, if you wanted to get more potential difference, you could connect multiple of these batteries in series with one another, right? So, all right, so going back to the lead acid storage battery, right? We have a lead anode, we have a lead oxide cathode, and both of them are submerged in a solution of sulfuric acid. So let's take a look at the half reactions that describe what's going on and how electricity is generated from a lead acid storage battery. So these are the half reactions right here. Get myself out of the way there, right? So in your anode, right, that's the stuff that's made of lead, right? The lead is oxidized by sulfuric acid, or in this case, the hydrogen sulfate ion. That's just the conjugate base of sulfuric acid. Got a donation from Roberto. Thank you very much, Roberto, for your generous donation. And yeah, if anybody would like to follow in his footsteps and support the stream, that would be greatly appreciated. There's a couple of ways to do it. You can donate via Streamlabs like Roberto just did. There's a link down there that says in the description that says support the stream. I also have YouTube super chats enabled, super stickers, things like that. Or just, leaving a like on the stream and offering some words of encouragement is another way that you can support the stream. It doesn't cost you anything. So, all right, thank you. All right, so back to the half reactions associated with the lead acid storage battery, right? So you have lead. undergoing oxidation by the hydrogen sulfate ion, right? And that produces lead 2 sulfate, this PbSO4, right? And then if you look in your cathode reaction, your reduction half reaction here, you have lead oxide also reacting with hydrogen sulfate ion, right? But instead of undergoing oxidation, it's undergoing reduction, but it's also producing lead sulfate, right? So you have the production of lead sulfate not only in your anode, but also in your cathode, right? And so if too much of that lead sulfate accumulates on the surfaces of your electrodes, then you won't get the flow of electricity and the battery will die, right? But luckily, this battery can be recharged, right? And the way that the battery gets recharged is by supplying electric current to drive the reaction in the reverse direction, okay? So if you supply some electric current, which usually in a car will come from the alternator of the car, right? That'll drive the reaction in reverse, and the lead sulfate will be produced, or it'll undergo the reverse reaction to produce just the lead that you started with, and also the lead oxide over in your cathode, right? So that's how the lead acid storage battery works, and that is how it gets recharged. You supply electric current to drive the reaction in the reverse direction. All right, so moving right along, we're actually getting through these pretty quickly. This might be a fairly short stream, but that's okay with me if it's okay with you guys. So, all right, so that's the lead acid storage battery. Now we're going to move on to a different type of rechargeable battery called the nickel-cadmium battery, or simply the NiCad battery, okay? So this was kind of the gold standard of rechargeable batteries for quite some time, but it recently has been replaced with a different kind of battery that we're going to look at on the next slide, right? So the nickel-cadmium battery, again, it's a rechargeable battery, right? And it's composed of a cadmium anode. Your anode is made of cadmium, right? And your cathode is made of a substance called nickel oxide hydroxide. So you see this whole NiOH species right here? That's called nickel oxide hydroxide. So that is what your cathode is made of, right? And so cadmium gets oxidized and it forms under basic conditions, and it forms this cadmium hydroxide, right? Nickel oxide hydroxide is reduced to form nickel hydroxide, right? And eventually, if the battery isn't recharged, you'll get too much accumulation of your cadmium hydroxide and your nickel hydroxide on the surfaces of your anode and your cathode, respectively. And the way that you recharge this, very similar to the lead acid storage battery, is you connect it to a charger that supplies electric current to drive the reaction in the reverse direction. Now, the important thing with recharging a rechargeable battery is knowing when to stop, right? Once you've completely regenerated your reactants, right, by charging the battery, you're just regenerating the stuff that's over here on the left-hand side of these half reactions. Once you've done that, charging should stop, because if you continue to supply electric current to this, you'll produce these unwanted side reactions, which could involve the electrolysis of water to form hydrogen and oxygen, which can be dangerous and it can cause an explosion. But the way that people have gotten around this is by installing sensors in the chargers that detect differences in voltage and temperature that basically tell the charger to stop charging the battery when charging is complete, right? So that's the nickel-cadmium battery. But again, this is kind of antiquated, right? There's sort of a new, improved version of this battery that is currently available. And the reason why this battery is not really the ideal battery is because cadmium is a fairly toxic element, right? So if you start producing all these batteries with cadmium in them, you have to deal with that toxic cadmium, and you have to find a clever way to dispose of it, right? So the replacement for the nickel-cadmium battery is something called the nickel metal hydride battery, okay? And these half reactions for the NiMH battery, as it is called, are shown here. Notice that the reduction half reaction for this NiMH battery is the same as the reduction half reaction for the nickel-cadmium battery. right? The cathode reactions between these two batteries are the same, but it's a different anode reaction. It's a different oxidation half reaction. And one of the interesting things about the nickel metal hydride battery is that it's actually kind of the standard type of battery that's used in hybrid electric vehicles, which is why I have this image here. Pretty funny South Park episode, like back when South Park was good, where everybody was driving hybrid cars around and they were all like really full of themselves. It's a good episode. I'd recommend checking it out. Roberto says, I used to find those nickel battery and RC car toys. Yeah, I think I used to have like a little drone. It was like a cheap little drone, and I think it ran on a NiCad battery, but I don't know. I'm not sure if it really did or not. I'd have to dig it up and look at it. All right, so how does the nickel metal hydride battery work, right? So basically what you have is you have a metal, right? A metal alloy that has hydrogen atoms held within it, right? And so this M here, that represents a metal, right? And this M.H represents a metal alloy that has hydrogen atoms held within it, right? And so that thing, this metal hydride, right? This metal alloy with hydrogen atoms in it, what it does is it undergoes oxidation to produce just the metal with the hydrogen removed. One of the products of this is water, right? And then, like I said before, the reduction half reaction is the same as the one that we looked at with the NiCad battery, where you have the reduction of nickel oxide hydroxide into just nickel hydroxide, right? So again, this is a much better battery because you don't have to deal with all those, disposal problems associated with disposing of cadmium, which is fairly toxic, right? All right, so there's the nickel metal hydride battery. And again, just like the NiCad battery, it is rechargeable, right? Which is, again, it's one of the reasons why it's so attractive as a battery that's used in hybrid electric vehicles, right? So, and again, you recharge the battery by supplying electric current, driving the reaction in the reverse direction to regenerate the reactants after they've reacted to form products. So that's how that works, right? All right, so we're going to move right along and talk about the next type of rechargeable battery. And you might be familiar with this one. It's called the lithium-ion battery. And the exact details of how the lithium-ion battery works are pretty complicated, but I'm going to try to explain sort of a simplified version of how it works, right? So again, just like any voltaic cell, you have an anode and a cathode, right? In a lithium-ion battery, your anode is composed of graphite with lithium ions embedded within it, right? And so they call it looks like in this diagram, they call it lithium carbon, lithium, carbon, graphite, whatever, right? So you have this graphite with lithium ions embedded in it. And then over in your cathode, you have a lithium, usually like a lithium transition metal oxide, like a lithium cobalt hydroxide or a lithium manganese hydroxide or something like that, some lithium transition metal oxide, right? And when this is discharged, in other words, when this is connected with something, what happens is your lithium ions start to migrate from the anode to the cathode, right? And that migration of lithium ions from your anode to your cathode causes a corresponding flow of electricity in your external circuit, right? So that's how it works. So that's a simplified version of how a lithium-ion battery works. And we are going to move right along once again. Like I said, the stream probably isn't going to take very long, but we're going to move on anyway. So the next type of battery we're going to talk about is called, actually, you know what, before we get into that, I forgot I had this slide here. This is a table that is basically like a comparison of all of the rechargeable batteries that we've looked at so far in this presentation, right? You have the NiCad battery, the nickel metal hydride battery, the lithium ion battery, and your lead acid storage battery, right? And the energy densities of them are shown here. So energy density is kind of like, you can think of it as like the amount of energy per unit mass of these different batteries. Notice that the energy density of the lithium ion battery is higher than the rest of them. And the reason for that is because lithium is a very, very low dense, it's actually lithium is the least dense metal in the entire periodic table. So that's why lithium ion batteries are so attractive, because you can put them in like phones and laptops and things like that. and it doesn't add a whole lot of mass, but it produces a lot of energy, right? So the energy densities and the overcharge tolerance, how well the voltaic cell responds to being overcharged, are all shown in this table here. So I invite you to look at this table and sort of study it at your own leisure if you like. All right, so that's that. So the next type of battery that we're going to take a look at is something that's actually pretty cool. I think it's really cool, and it's called the fuel cell. Okay, so a fuel cell is kind of a unique type of battery, right? It works a little bit differently than the batteries that we've seen so far in this presentation. Unlike the batteries that we've seen previously in this presentation, the fuel cell is configured such that the reactants have to be constantly replenished. They flow through the reactor, so to speak. They flow, like the reactants flow through the battery continuously in a fuel cell, right? So over here, so this is like a little car that's sort of powered by a fuel cell. So that's kind of a cool little thing there. And then over here, you have a diagram of the most common type of fuel cell, which is the hydrogen-oxygen fuel cell, right? And so you see here that you have hydrogen being pumped in over here. In your anode, the hydrogen undergoes oxidation to form water, right? And the oxygen over here gets pumped in to your cathode. And these reactions in your anode and your cathode of your fuel cell are facilitated by the help of a catalyst. Usually it's a platinum catalyst that catalyzes these reactions, right? So you have hydrogen being oxidized to water, and then you have oxygen being reduced to water in this hydrogen-oxygen fuel cell. So let's take a look at the half reactions of this cell, okay? So again, it's pretty straightforward. I didn't mean to do that. Hang on. So again, it's pretty straightforward. In the anode, you have the oxidation of hydrogen, and it's under basic conditions, so that's why you have these OH minuses over here. And this produces water and electrons, of course. And then the reduction half reaction, you have oxygen being reduced, right? Now, if you take a look at these two half reactions and look at them closely, you'll see that the 4 hydroxides over here on the reactant side of your oxidation half reaction cancel out with your 4 hydroxide ions over here on the product side of your reduction half reaction. And so literally the only product of this reaction is water, right? So fuel cells are like really green, right? I mean, at least they seem to be on the surface because the only product of the reaction is water. In fact, in the space shuttle program where you have like astronauts, you know, up there in space, they'll use fuel cells to generate electricity inside their space shuttle, and then they'll literally drink the water that is generated as a byproduct of the fuel cell redox reaction. So that's something that's kind of cool, right? And the fuel cell can actually be scaled to about the size of like a refrigerator. So if you have a fuel cell that's about the size of a refrigerator outside of your house, that can supply more than enough energy to power your entire home. And also, you know, the water that comes out of it, you know, you can water plants with it, you can drink it, you can bathe with it, or you can do whatever it's just pure water, right? And so you might be asking yourself, well, if fuel cells are so great, why do I not have one at my house? And why does my car not run on a fuel cell? And the answer to that question is like the big problem with fuel cells, the big hurdle in developing the technology is finding a better, more readily available source of hydrogen gas, right? Oxygen, pretty easy to find. It's like, what, like 18% of the air or something like that. So you can easily get oxygen. It's very abundant in our air. Hydrogen, not so much. There's none of it in the air. I think most of the bulk industrial production of hydrogen gas involves stripping hydrogen off of hydrocarbons like methane and natural gas and stuff like that. So just because something runs on a fuel cell doesn't mean that it's like super green and super carbon neutral, right? Because that hydrogen has to come from somewhere, right? And chances are you probably burned some carbon in order to get that hydrogen, or you stripped it directly off hydrocarbons, which, like I said, that's the biggest sort of bulk operation of the production of hydrogen gas. So that's the fuel cell. Pretty interesting. I mean, like I said, it's got a long way to go before everybody just disconnects from the power grid and we all have fuel cells powering our homes. That would be pretty cool, but they have to, they have to come up with a better source of hydrogen that's more readily available. All right, everyone. So kind of a short stream, but that's going to do it for me. I just wanted to have a stream where I devoted the entire thing to talking about batteries, which I don't know. I've been excited about this one for a long time because, I know chemistry can kind of get a little abstract and, we kind of veer away from real life. But this is like one aspect of electrochemistry that's very, very relevant to our lives. I mean, everybody has a cell phone with a lithium ion battery in it. Everybody, anybody who has like an Xbox controller, you put AA batteries in that, right? Those are all voltaic cells. This is the stuff that we've been learning about that we know really, really well from like a bottom up sort of perspective. So I really, really hope you found this stream valuable. Thank you very, very much for watching. We still have a couple of more topics within electrochemistry to cover. So this will not be the last electrochemistry live stream. We're going to do another one next Sunday. So what's that going to be? Sunday, the 17th, April 17th. That's going to be the next live stream. So I hope to see you guys all there on the 17th, 9 o'clock p.m. Eastern time, as always. And all right, take care.